Hi, I'm Jeff. I'm with the Teen Advisory Board for the Howard County Library System. And today I'm going to be talking to you about combinatorics. Specifically, I'm going over factorials and permutations today. So, prerequisites really all you need to know is maybe a basic understanding of algebra, and also you just need to know how to count. So if you can count 1, 2, 3, 4, 5, you're pretty much good to go. So let's get started. So consider this problem here. A group of friends decides to have a Stars Brawl tournament during lunch. There will be 5 games played, but the students are struggling to organize the schedule. How many different schedules are possible? So by schedules, we mean ways that we can order these 5 games. So if we call these games game A, game B, C, D, and E, this right here is one possible schedule. So we just go A, then B, then C, then D, then E. So the question is asking how many different possible orderings can we have? So one way we can approach this problem is just by counting all the different possibilities. So B, A, C, D, E might be another option. B, C, A, D, E. And then we could really just go on, but this strategy might take a lot of time. So I'm kind of lazy, so I don't feel like doing that. So we're going to go back and find a faster way to solve this. So if we think about this problem, basically what it's asking is we have 5 different time slots and 5 different options for each time slot. So if we go through the first time slot, we have 5 different options. We can either put A, B, C, D, or E in the first slot. So second slot, similarly, we can put anything we want, except it can't be the same as the first slot because we can only use each game one time. So if we choose the first slot first, that means that our second slot, we will only have 4 options, no matter what we choose for slot A or slot 1. And similarly, for the third slot, we only have 3 possible options because we already picked some games for the first 2 slots. And similarly, for the second to last and last one, we only have 2 and 1 left. So what these numbers mean is that they each mean that for that slot, we have that number of possible things we could put in that slot, assuming that all the slots before it were filled. And so we want to know the number of ways we can do this. So we would then have to multiply all of them together, because for whatever game that we put in the first slot, we can repeat this process and put 4 different games for the second slot and so on. So we would be multiplying all of them together. And yeah, and that would give us our solution, which is 120 possible orderings. So what we really did just there was a factorial. So a factorial basically is an ordering, is the number of orderings of n different items into n different slots. And we represent it using the exclamation mark notation. So basically, if we have 5 factorial, which is what we just did, that would be 5 times 4 times 3 times 2 times 1, which in other words is just the number multiplied by every positive integer before it, all the way down to 1. So similarly, 4 factorial would be 4 times 3 times 2 times 1, and so on. So one key distinction here is that 0 factorial is actually equal to 1. So that might sound a little bit weird, but the reasoning basically is that if we have 0 games, we have exactly 1 possible ordering, just don't have any games. And that would be the 1 ordering there, which is why 0 factorial would be equal to 1. All right, so let's take this and kind of apply it to a little bit different of a problem. So let's say some more students want to join our tournament. So they propose that there are 5 additional games that they want to add to the existing 5 games. So that would bring us to a total of 10 games. Except the hosters of the tournament, they still only want there to be 5 games in the schedule. And we're asked the same question, how many schedules are now possible? So what this means is that instead of having 5 games we want to fit into 5 slots, now we have 10 different games. Just pretend all those are a game, and we want to fit them into the same 5 slots, but we can only choose 5 of them. So now it's not just the ordering that matters, it's the ones that we choose. But we can really think about this problem the exact same way. So for the first slot here, we have 10 possible games that could go there. After we eliminate one of the games, the next slot, we only have 9 possible options. For the one after that, we would only have 8 possible options, 7 for the next one, and for the final spot, we will have 6 possible games remaining. Again, like all the games, there's no difference between them. It doesn't matter which one we pick, but we know that for these 5 slots, for the first one we would have to pick 1 out of 10. Second one, we're given a choice 1 out of 9. Third, 1 out of 8, and so on. So if we multiply these together again, we get our new answer for the total number of schedules, which is a pretty big number. If you want to plug that into a calculator, go ahead. Actually, I'll just do it here. So it would be 10 times 9 times 8 times 7 times 6 times, which would be 30,240. So that's a lot of schedules. So good thing we didn't try to count all of those. So what we did there is something called a permutation. So a permutation is really similar to what we're doing with a factorial. It's just that now with a permutation, we take into account that we might have a different number of elements that we want, as opposed to the total pool of elements that we can choose from. So in other words, we had n different elements here where n equals 10, and we only had k slots where k equals 5. So that means what we really had was n equals 10, so 10 factorial over 10 minus 5, which is 5 factorial. And if you expand that, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we can just simplify that as 5 factorial. And we divide that by 5 factorial. 5 factorials cancel out, and we're left with 10 times 9 times 8 times 7 times 6, which was our answer for this previous problem. So that's a permutation. That's when we care about ordering, and there might be more elements to choose from than the number that we actually want to choose. So factorials and permutations, they're both really central to combinatorics. And next video, I'm going to be going over another really central topic in combinations. So thanks for watching. Hope you enjoyed, and I'll see you in the next one.